Thank you, everyone. I am so pleased that you could all join us today. My name is Gail Powley. I'm president of Technology Alberta. And as Amy and the AI seminars are quite gracious to provide us the platform once a month to showcase tech companies across the province that are actively using AI and hiring AI graduates. Chris is a great example of one such company in that he not only is he growing his company in Alberta, but he's actually currently working with Technology Alberta in the First Jobs program that was designed with people from the U of A and in Calgary to keep our great AI talent here in Alberta. So without further ado, I'll let Chris introduce himself and turn it over to you and to talk to us about Pulse Medica. And please do brag, Chris, because you're quite a success story. Continue. Over to you.
Okay. Thank you, Gail, and thank you to Amy for inviting me to talk. So as Gail said, so I'm Chris from Pulse Medica. So I'm the lead machine learning engineer. So Pulse Medica is a medical device startup. We spun out of the U of A about 2 years ago from a photonics lab. And so our main focus is on retinal disease, treating a little bit of diagnostics surrounding retinal disease. So we have around, I think, 14 or 15 people full-time, and about 4 or 5 of us are focused on AI. So we recently had our latest raise, and so our team is growing. I expect that we'll be growing quite a bit more over the coming years. As Gail said, we've been participating in the Jobs First program, which has been a great experience for us and a great way to find talent here in Alberta and keep it here. So today I'll talk about some of the projects we've been working on. So like I said, our focus is on retinal disease. Let's see, there we go. So I'll talk a bit about some of the projects we have. So specifically semi-supervised feature detection or segmentation relating to retinal disease, as well as some other projects like floater detection and some other things we've been working on related to histology and general object detection. But quick, I'll just summarize the medical side. So what are we talking about when we say retinal disease? What are the issues nowadays? What are we trying to solve ultimately? So around 500 million people worldwide suffer from some kind of retinal disease. In particular, diabetic retinopathy is one really bad culprit. So it affects people who have diabetes, and around 40% of the people who have diabetes are diagnosed with diabetes already have diabetic retinopathy. So diabetic retinopathy is so typically it damages blood vessels and also results in the growth of irregular blood vessels, which then leak and then damage surrounding tissue. And eventually this disease leads to blindness. The current treatment is not fun. So typically they'll use injections into the eye, and this will repeat every few weeks for the rest of the patient's life or until they go blind. So it's not very effective, and it's also very expensive. An alternative is to use lasers, but current laser technology used for this is typically it means sacrificing a significant part of the patient's vision. So this grid laser approach will basically sacrifice 80% of the patient's vision in order to preserve the patient's remaining 20% and prevent progression of the disease. So these are the main challenges that we're trying to address. The way that this disease is diagnosed is through imaging, retinal imaging. So 2 popular methods are using something called a fluorescein angiography. So this is a dye-based strategy where they inject a dye into the patient's arm, and then that'll give you really high contrast of blood flow. And so that will and typically result also in a sequence of images where you can see the blood flowing through the veins and blood vessels, and you can see the leakage, as well as OCT or SLO. These are laser-based imaging methods, which will give you a 2D and a 3D volumetric scan of the retina. which also lets you calculate the retina thickness, which is a super important quantity and metric for detecting leakage. Leakage we usually have a thicker retina area. So the current process for diagnosing and treating diabetic retinopathy is the ophthalmologist will take all these different modalities, so the FA, fluorescein angiography, the SLO, OCT, maybe a fundus, which is the optical method you see in the back, and then look at other things like where in the image is non-perfusion, so dark areas which are showing where blood is not getting to, and so that indicates that those cells are dying off, and that's prime areas for treatment, as well as areas of bleeding or leakage. And so MA, or the irregular blood vessels near areas of leakage, are really the key ones that we want to treat. And so based off of that information, the ophthalmologist will either decide no treatment, they might diagnose, or they might prescribe some vitamins, or they'll give them anti-VEGF injections. These are basically injections that will prevent the growth of those irregular blood vessels, and that repeats indefinitely. Or they'll do some kind of grid laser or focal laser, which will sacrifice patient vision in order to prevent the progression of the disease. So when using lasers to treat diabetic retinopathy, really what we want to target are these microaneurysms. So these little white dots that appear in the FA, fluorescein angiography. And so these are the areas of those irregular blood vessels which are causing leakage and causing the progression of the disease. So instead of using a laser, which essentially broadly photocoagulates the entire peripheral area, at Pulse Medica, we're developing a software and hardware system to accurately use a computer-controlled laser to photocoagulate just these specific microaneurysms to provide a more permanent treatment while also preserving as much vision as possible. But a major issue here is how do we know where to aim the laser? We need to find all these targets. And in some images, there can be hundreds of them. And so for that, we've turned to machine learning. And so machine learning has already been shown to be really good at segmentation. So this is using a CNN convolutional neural networks. And this is semantic segmentation, which means you're looking at an image and you're segmenting objects based on the pixel by pixel mask. And so this is a supervised method, meaning that you've had someone go through these images and hand outline each of the different objects, and then use all that data to train a model to do the same thing quite accurately. And this approach is also commonly used in healthcare, where in this example, they're using semantic segmentation to identify tumors in a brain CT scan. But in our case, it's a lot more difficult because in these images, there can be hundreds of microaneurysms. So you have these tiny little features, and each patient can have a set of 20 of these images, and you need thousands and thousands to train a model. So to have an ophthalmologist to sit down and accurately sketch out every single pixel associated with diabetic retinopathy isn't really practical, since typically ophthalmologists are incredibly busy and their time is extremely valuable. But at the same time, we need the ability to identify these treatment targets to build an automated system. So an analogy for this is you have an image with a giraffe and you want to build a model which can identify the giraffe in the image. The conventional approach is you collect thousands of images and then you find some people, maybe some giraffe experts, who can go through and hand annotate the locations and the pixels of those giraffes, and then you train a model which can then reproduce that and detect giraffe pixels in any image. But now let's say your image is a lot more complex. Instead of just having one giraffe, you have all kinds of animals and they're all over the place. And now it becomes a lot more difficult to have someone go through these, and it's a lot more cumbersome. And it can be more time consuming. And even this image is a lot easier to do than fluorescein angiography with microaneurysms. So our approach is to essentially remove the need for hand annotation altogether. So the typical approach or the conventional approach is you have that expert hand annotation and then maybe review process, you train your model, and you end up with the detection model. Our strategy is to just use the images themselves, along with the diagnostic labels. So it could be whether a patient has a disease or not, or other labels that demonstrate connections between patients or with certain diseases, and then train a model based off of that can predict these labels, and then extract information from this trained model, which can then be used as a segmentation model. So a simple example is if you have a dog-cat classifier. So assuming you have 10,000 images of each dog and cat image, and you know for each image if it's a dog or a cat, but you don't have any annotation. You don't know where in the image each animal is. So we can use this to accurately classify dog or cat. But what if we want to know where the animal is in each image without having someone go through and sketch that out for us? So one approach you can use is sometimes called explainability, attribution, or interpretability. And basically you can go through each pixel and say, does this pixel, what effect does this pixel have on the prediction of our model? And you can express that as a simple partial derivative where you're finding the incremental change in a prediction at the output versus an incremental change in one of your pixel values at the input. And so if you do this for every single pixel, you can build out this kind of attribution map for each image. And so this will kind of work. You'll see some relevant features in each image, but you also lose a lot of the content that we as humans know is important in identifying visual features and making that classification. Also, you'll get a lot of irrelevant features, such as you'll get noise in the background. And so the reason why that happens is that, well, there's two main reasons. One is that the input gradients that we calculated don't directly reflect the relevancy of those pixels. And that's because models are deep learning models are very nonlinear, and they can, you'll typically lose a lot of resolution as you propagate signals through them. But also the model itself won't necessarily take into account all the features that we would as humans when identifying objects. If there's a simple way to focus on areas of high contrast, like the eyes in this case, where it puts a lot of weight, then it'll do that and ignore the rest of the image. And so this is fine if you're building a classifier, but if you want a segmentation model, it's not very desirable. You want to be able to capture all of the relevant features. And so that's where a lot of our energy has gone, is how do we, in one case, so how do we better calculate that attribution to better reflect the relevant features, as well as how do we adjust the model structure and training strategy so that we preserve as much detail and can attribute as many pixels that are relevant as possible in our final attribution map. So going back to retinal imaging, so on the left here is the fluorescein angiography with the microaneurysms identified in red. And so without any hand annotation, we're able to pretty accurately pick out the microaneurysms of interest without the need of having someone go through and mark those out for us as training data. So other related areas of interest. So in retinal imaging, you have non-perfusion areas. These are areas of darker contrast or darker areas where blood flow is essentially cut off. And those are super important when deciding where and when to treat, as well as detecting retinal leakage. And so those are key indicators as well. That means that the microaneurysms nearby there are causing a lot of damage and are prime candidates for treatment. And so using somewhat similar approaches, we're able to use machine learning to identify these areas. So this is for non-perfusion, as well as identify some key leakage areas. And then we can cross-reference that with the detected microaneurysms to build a complete picture for the ophthalmologist. So the ultimate vision is that we take the fluorescein angiography image, we can then detect our microaneurysms, with our semi-supervised method, and then also do the similar thing for non-perfusion and leakage, and then combine that with other modalities like OCT and SLO, which will give us the thickness map, and then present this kind of all-in-one image, which overlays all this data that the ophthalmologist can look at and decide where to treat without having to juggle all these different images. And we can also use this data to help build automatically a treatment map and a treatment plan for an automated laser treatment system. So in the meantime, though, we're incorporating this into a diagnostic software. So we launched this, essentially, we have a container for our models where the ophthalmologist can upload their images, and then we'll process them in real time and then present them a summary of which microaneurysms are the highest probability to cause damage and the highest priority for treatment. And so currently we're beta testing that at the ARC clinic, so Edmonton's largest retina clinic. So similar, another problem, which is kind of similar, so the detection of floaters. So you probably have seen floaters before. If it's a bright day and you're looking at a light surface and you see like the little squiggly things float through your field of view. So those are actually small strings of tissue that are suspended in the vitreous of your eye, sometimes parts of the retina that have detached. And for some people, floaters can have a huge impact on their vision. And right now, there isn't really an effective and safe way to treat floaters. But if you could accurately target these floaters with laser, then you could potentially destroy them. But in order to do that, you need to be able to accurately detect them and track them in real time. So, but to do that is fairly challenging. So this is an SLO image. And so in this image, there are a bunch of floaters, but just looking at it, it's almost impossible to see where those floaters are because there's so low contrast. And what you're actually seeing, if there are floaters, for example, here's one up here. This is actually just the out of focus shadow of a floater. But if we could track that accurately, we could find that in 3D space. But there's some big challenges with that. For one thing, typically for object detection or object tracking, you're looking for changes in or areas of significant contrast. And if it's tracking, you're looking for how that changes over time. But with floaters, you don't really get a lot of contrast. You'll typically just get kind of blurry gradients. So we've developed a method which uses, so it's a model structure which is adapted to these kind of out-of-focused features that you'll get when you have floaters moving around in someone's eye in these SLO images. Then combine that with some statistical methods where we can accumulate information about how these floaters are moving around, and we're able to get a fairly accurate detection method and tracking method for these floaters. So the idea is that once you are able to track their motion, then you can use the OCT laser to find them in 3D space and then potentially treat them. So some other directions, we talked about retinal imaging. We've also looked at some other applications for this semi-supervised object detection, such as in general purpose object detection, as well as in histology. So in histology, it's kind of a similar problem with some other hurdles. So here you have a slide that consists of about 186,000 by 88,000 pixels. And so that's far too big of an image to put into a model and try to identify things. But if you look closely, so this is a, I think 1024 by 1024 image tile, you can identify the parasites here. So we have a collaboration with a lab testing company here in Alberta to basically build a screening tool for Giardia. So Giardia is a parasite, and the process of screening Giardia is very cumbersome. So if you could build a tool that could do this very quickly without needing a huge amount of annotation and hand labeling, then that could be really attractive to reduce the workload for these technologists who scan through these slides with a microscope, essentially. So we're able to use a similar strategy to build a screening model for this. So we got fairly high accuracy for these tiles and a very low false negative rate, which is really the key parameter. You want to, it's fine if you get it wrong and have a false positive, but if you have a false negative, then someone's disease slips through the cracks. And so that's what you want to avoid. And we're able to build out these detection maps. So with the healthy slide on the right, you can see highlighted in green, basically there's no floaters detected, or sorry, no Giardia detected there. Whereas in the positive Giardia side, you get a lot of positive hits for parasites. And so this is a way where we can ease that workflow, where someone going through here can just pick out the regions of potential parasites and save a lot of time. Yeah, so in conclusion, we focused a lot on semi-supervised methods for feature detection with very little human input. And our main focus has been on diabetic retinopathy, but we're currently working on extending this to other retinal diseases like glaucoma, VMT, and also we're moving towards the real-time tracking and detection of floaters, which we think could really have a big impact since there's no existing method for both tracking them but also treating them. And we're also at the same time exploring some additional applications in histology as well as some other leads. Yeah, and so all of these have been growing very quickly over the last year, and our team's been growing very quickly as well. So thank you to the Pulse Medica ML team. And hopefully the list will be a lot larger in a few months or in the next year at least.
Excellent. Thank you so much, Chris. Anyone who has any questions, you can put up your hand. I also had mentioned you can put the questions in on the chat. And then Chris, overall, you know, it is exciting to know of how the Pulse Medica has been in the news over this last couple of weeks. So if you were to just look out in the next year or so, what do you think how do you think Pulse Medica will change over this next year?
So I think as we're going along, we're realizing how big the potential is to have an impact just in the ophthalmology space with AI. So I foresee our team's going to be growing a lot, and we're going to be going after a much wider spread of applications, both on the diagnostic and the treatment side. And I also think that so as we get more as we grow and get more recognition, the opportunities to partner with larger companies, especially the ones who manufacture these imaging systems, becomes easier. And that really opens doors for where we can exercise these things we come up with. And so, yeah, I'm really excited about that.
Outstanding. And so if people want to contact you, you do have your contact information on the screen. I'm going to have to ask you to stop sharing your screen, so if you can put that in the chat. But you had also said that people can link in with you as well, right?
Yeah, definitely.
Excellent. And I'll say, Russ, if you are available, I'm just going to help Pushkar with the sharing the screen on this side. So if you have any questions, I see your audio is connecting. So looks like we have some station identification here. But also, Chris, do you have any messages to the students, the researchers on AI, what they should be looking for? And, oh, I see Russ is back. You're back, Russ.
Well, that was a wonderful talk. Thank you very much. A lot I want to learn more about. This idea of using the semi-supervised method, that I'm curious how you showed an example, but what techniques are you using to do that?
Sorry, could you repeat the last part?
I'm just curious. I was impressed. It seems to be actually working. I would have thought it. I'm curious to know what specific techniques you were using. Are they published someplace? Are there things which are still proprietary? How do you find the little spots that are unusual in this very complicated shapes and textures?
So the specific techniques, that's where it gets a little awkward because like I'd love to talk about it, but I'm kind of handcuffed a little bit in what I can say about the details. But in its essence, it's so are you familiar with those kind of explainability or interpretability approaches? Yeah. So so if you just try that out of the box, it probably won't work.
Yes.
You're not going to get selectivity, and you're not going to basically find the smaller, less important microaneurysms. So the main challenge then is, so I think I had a slide there that talked about, so first of all, how do you get the best representation possible of what the model's actually doing and thinking? But also, how do you encourage the model to take into account everything that's relevant rather than just picking up on a few key things? And so, probably without my CEO getting too angry at me, I can say that a lot of it had to do with how you construct the connections in the model so that you can, and the criteria, the loss criteria, so that you motivate the model to spread out its attention to all these different features.
You have prior information that says I'm looking for small white things. Is that implicit in it, or
Sorry.
Do you put any prior knowledge in that the shape of thing that you're looking for at some level that's explicit, or is that a question that gets too detailed?
So no, we don't. So the model doesn't know anything off the bat about what it's looking for.
Okay. Wow. Well, again, if you're able to talk about it, I'd love to hear more about how it gets that to work, but I should be quiet and let Randy ask questions. I see
Randy has a question. I see that.
Russ and Randy are always the question askers. So one thing that you might want to do, Chris, is thanks for the talk. I admire how calm and deliberate you were in delivering it. That's exactly the antithesis of Randy talks, where he's jumping up and down and screaming and yelling and stuff like that. So I appreciate your presentation for that, as well as the content. One thing you might want to do you know Hussam Babakar?
No, I don't.
So he's a graduate student working in our explainable AI lab. He's a guy that you would like to have a conversation with. So if you send me email, then I'll connect you to. The question I have is a medical one, not a machine learning one, and it's about floaters. You mentioned that floaters are tissue. Is that always the case, or are floaters the result of sort of organic chemistry imbalance that creates some coagulation of molecules?
So that might be true. I actually don't know.
Okay.
Yeah, sorry, I'm not an expert on the medical side.
Okay.
I'm just, yeah.
The reason I ask that leads to the real question I wanted to ask, which is alternative treatments. So the value of what you're doing in finding crisp boundaries of things you can target with lasers is what I see as sort of the business model. What do you compete with regarding alternative treatments? What are the alternatives?
So there's very little. So as far as I know, there's one laser-based method for treating floaters, which is almost never used by anyone because it uses kind of a conventional laser approach, which is quite dangerous. There's a high chance of damage to the retina. Yeah.
Okay.
So our strategy is basically to, I'm not sure, but we use a different laser type that avoids that issue if we can accurately track it.
Do you also, in the images you showed, I couldn't tell whether you were identifying floaters in 3 or even 4 space. Can you do that? And I would guess the ophthalmologist would love to see a movie about where the floaters are moving around, for example, and how big they are. Can you do that?
Yep. So that's the end goal. The first step is to kind of, so what you're seeing in that SLO is basically a projection of everything in the retina or everything in the eye up to that point.
Yeah. Okay.
And then And then utilize, once you have those coordinates, you can utilize a volumetric method to find where it is in 3D space and then build a kind of 3D representation.
Okay, thank you.
Excellent. Thank you so much, Chris. And I see some questions in the chat from people who want to learn more about AI and machine learning. Amy and the U of A AI department are certainly the experts, so please do check out their website. And Chris, thank you again today. And everyone, you see Chris's contact information on the chat, and you can link in with him.